Salut tout le monde, welcome back to my channel. I'm Anthony, obviously, and you are currently watching episode 43 of me reading Differential Geometry by Erwin Kreisig out loud, on screen for all of you to both watch and or listen to. And I'm just gonna get right into it. So I filmed for like an hour earlier, was Starbucksed out, and then I realized I really didn't say anything that moving or important. So this is one of the longer sections left in the book because we're in the last chapter, chapter 8, Special Surfaces. But really this is a lot of discretionary material on behalf of Erwin Kreisig. So with that being said, it involves a lot of complex variables related topics, maybe because he's influenced by Stefan Bergman at the time when he was writing this. They were both at Stanford around then, I believe, and the complex variables was thick in the air at the time. So chapters 1 through 7, basically once you got past like the lectures on differential geometry for like an undergrad level, if you will, then he delves into like this kind of more monograph style. And like I said, there's a lot of complex variables. So a lot of the chapters or sections, I keep on messing that up. I'll refer to sections as chapters. But anyways, the sections will sometimes be only a single page. There's like 1 or 2 sections that have been that short. A lot are about 2 to 3, 5, 7 pages, somewhere in there. And then a lot of the chapters were pretty well broken down, but then this last chapter is like 20 sections. So we have 16 sections left. So it's like, yeah, we are in the last chapter, but also there's like 2 chapters, 1.5 to 2 chapters left based upon the average lengths of the previous chapters. So, you know, if this is a longer section, not really the time for like an hour-long rant about formula sheets and Neo-Pythagoreanism and stuff like that. So anyways, section 84, modular surfaces of analytic functions. Let lowercase h of z equal a sum on alpha from 0 to infinity of a sub alpha, then times the quantity z minus z naught closed quantity to the alpha. Let this lowercase h of z be an analytic function of a complex variable z equals x plus iy. We set h of z equal to capital U plus I times capital V equal to capital W, then times e to the I gamma, lowercase gamma. That is, we denote by capital U and capital V respectively the real and imaginary part of the function h of z, and by w and gamma respectively its modulus and phase. This should all be very familiar to the differential geometry gang. We're already up on complex variables around here. So moreover, we introduce the following notations. A sub alpha equals capital A sub alpha, then times e to the I beta alpha. We also introduce z minus z naught equal to r times e to the I phi. Let x1, x2, and x3 be Cartesian coordinates in 3-dimensional real space R3. Then the vector parametric x is in terms of component x, component y, and also is in terms of that capital W in terms of x and y, where capital W is like the modulus of our complex exponential representation of h of z. So this is all a representation of a surface in R3, which is called the modular surface, or surface of absolute value of the analytic function h of z. I might as well just pull over here. I did rant for an hour, and I pulled up this other book, which I have next to me here. But I'm going to scroll to the relevant figures. Okay. Maybe it's good that I did another take. So this is right here, Visual Complex Analysis. This is a great book. I keep referring back to this throughout this like monograph section, this monograph on like crossover between differential geometry and complex variables in the last chapter, chapter 8 of Differential Geometry by Erwin Kreisig. I was ranting, I was like, I keep on referring back to this book because, okay, check this out. Figure 2, Figure 3, we were just discussing complex analytic function lowercase h of z, but okay, this could be lowercase f of z, and we're still talking about the same stuff here. So we mentioned modulus, that's capital W, and phase, lowercase gamma. Phase, you could also, I've seen called maybe like the argument perhaps, and then this modulus, it's basically like the complex magnitude. And you can compute that by doing this, right, like absolute value looking operation on it. And when you're in complex variables and you want to be technical, it's really the modulus. But that's why we have these modular surfaces, is because I've talked about it before where you could have a complex valued function. You could be loose with the terminology. It can mean a lot of different things. It could be like you have a real number and you have a function that takes that real number as an input, and then that provides as an output a complex variable in the form, you could say x plus iy. You didn't put in x or y, but x and y are real values in this case. Okay, that's one kind of like, you could say loosey-goosey, referring to a complex valued function. So you could take that and you can graph that, and you can get away with maybe just like a plane, because then you could say, okay, all of the points of an implicit domain plane map to this complex plane, and maybe you could like heat map, color it in or something like that, and you're like, okay, this is like a complex function. But really what we're talking about here in like this figure 2, figure 3, section 84 is like your input to the function itself is a complex variable. Then you get a complex variable out. So it's like, how do you visualize or like graph that? And so you can't really do that in a straightforward way. But what you can do maybe is like take this modulus, and then you can make these modular surfaces, right? And I feel like looking at figure 2, figure 3 is a way more obvious way of understanding that concept if you've never seen or heard of it or used it before, or if it's like it's been a while since you've read some math stuff in this subject area. So I thought I would just throw it out there from, I just said, oh no, I'm not going to do an hour rant at the beginning, but okay, that was maybe helpful out of it all. So anyways, examples of such surfaces of higher transcendental functions, gamma function, which, okay, and here's another rant, that gamma function that I just read, examples of other examples of such surfaces of higher transcendental functions. First example, gamma function. How do you represent that notation-wise? Oh, a capital gamma. Oh, and earlier in this book, we also have capital gammas are Christoffel symbols. You can say, oh, Anthony, why do you say Christoffel sub alpha gamma? Well, because that's why. You could have a gamma function in the mix. Maybe, yeah, in the actual application, it's like spherical harmonics, Bessel functions, blah, blah, blah. But it's like maybe that should be a trend. We should call, we can just say Christoffel symbols and be like Christoffel sub A, B, superscript J. I don't know. Food for thought. So examples of such surfaces of higher transcendental functions, gamma function, elliptic functions, cylinder functions, Riemann zeta function, etc. can be found in the book of tables of functions by Janke and MD. That's interesting that, it really dates this book, because once there's computers, books like that just don't exist. But that was like a thing that maybe like working mathematicians would spend their time putting together, like tables of logarithms and stuff, and be like, that's my work for the last grant period, you know what I mean? On the modular surface of a function, the curves of constant absolute value, capital W, and of constant phase, lowercase gamma, can be described. In this manner, we obtain a useful illustration of the behavior of the function for complex values of the argument. We may say that modular surfaces are analogs of the usual graphs of a real function of a real variable. There, what was I just saying? These surfaces are therefore of interest also in applied mathematics. The investigation of these surfaces by means of the methods of differential geometry, as it will be presented in the following pages, was made by Ulrich and his pupils, referred to the references in the bibliography, namely by the guys Ulrich and Zaat, Z-A-A-T. I actually think when I looked up all the guys in the bibliography, the guy capital Z-A-A-T was like the most, if I'm not mistaken, was like the most modern person who authored a work in the bibliography. So like literally everyone else was like a historical figure, like Gauss, Riemann, Minardi, Kadazi, Gaspar Mach, they were all historical figures up until, but then this guy's like, I'm pretty sure was born in like the 30s or 40s or something like that. So there's no like, he's basically just like a private citizen from like the view of the internet, essentially. There's like no info on him, but everybody else there basically is. So I actually think maybe it was like just his mathematical genealogy tree, but then that was like it. Anyways, we will now investigate some basic problems which will yield a general characterization of the modular surfaces. We start with the consideration of rays which are tangent to a point of a surface of absolute value. We call these rays half tangents. Theorem 84.1. At every point z0, which is not at infinity and is a point of regularity of the function lowercase h of complex variable z, other than a simple zero, the half tangents to the corresponding surface of absolute value form a tangent plane. The tangent in the direction lowercase phi star equal to beta naught minus beta 1 makes the maximum angle with the x1, x2 plane compared with all other tangents at our given point z0. Complex value, should I say. This angle is lowercase psi, or c. I don't want to say c because then it sounds like the Latin character after B and before D, but it's PSI. I'm pretty sure the correct pronunciation is C, but it's psi, psi, I guess, I don't know. Psi star equals the arctangent of the modulus of H prime evaluated at Z0. And to obtain this, we can refer back to previous expressions which are earlier in this section, which I already read. At every multiple zero of h of z, the function, the tangent plane exists and is parallel to the x1, x2 plane. If the given z0 is a simple zero of h of z, the half tangents at z0 form a cone whose generators make the angle c star, and we can refer back to what I just said for its definition above, with the x1, x2 plane. The proof is as follows. The problem consists in determining at z0 the derivative in a certain direction of a function of two real variables, almost like a directional derivative. We denote this derivative by the modulus of h evaluated at the given z0, but then the modulus itself is prime, and that's sub phi. Moving on, since we have this expansion here of f of z, which is equal to a0 plus a1 times quantity z minus z0, closed quantity plus O of r, which is equal to a0 plus a1, which again, these are subscript indices, a1 times r times e to the I phi, then plus O of r. Thus we obtain h bar of z is equal to a0 bar plus a1 bar, then times r times e to the negative I phi plus O of r. And if alpha naught is non-zero, therefore capital W squared is equal to h times h bar, which is equal to then capital A naught squared plus 2 times German character capital R, quantity lowercase a naught, then times lowercase a1 bar, then times e to the negative I phi closed quantity, then times r plus O of r. And this is equal to then capital A naught squared plus 2 times capital A naught, then times capital A sub 1, then times r times cosine of beta naught minus beta 1 minus phi closed quantity, that is of what cosine is evaluated on, plus O of r. Hence, capital W is equal to capital A naught, then times a quantity 1 plus capital A1 over capital A naught, then times r times the cosine of beta naught minus beta 1 minus phi, close all quantities plus O of r. We thus find that if we have the modulus of h of z naught, then prime on the modulus sub phi, this is equal to capital W sub r in terms of r and phi, then evaluated where r equals 0. This is equal to capital A sub 1 times cosine of beta naught minus beta 1 minus phi, which then is equal to the modulus of h prime evaluated at z naught, then times the cosine of beta naught minus beta 1 minus phi. From this, the statement involving what was above from theorem 84.1, the statement, we have phi star equals beta naught minus beta 1. From this, the statement involving that follows. What I just read as far as the modulus of h evaluated at z naught, then prime sub phi, this is the tangent of the angle C between the x1, x2 plane, and that half tangent whose orthogonal projection in the x1, x2 plane corresponds to the angle phi. From this, the other expression in the statement of the theorem follows, the one that is for C star. If z naught is a simple 0 of h of z, then lowercase a naught is equal to 0, and the modulus of h evaluated at z naught, then prime sub phi, is equal to the modulus of lowercase a sub 1, which is equal to capital A sub 1. In this case, the half tangents form a cone at this point. If z naught is a multiple 0 of h of z, we have that lowercase a naught equals lowercase a sub 1, which equals 0, and the modular surface has a tangent plane parallel to the x1, x2 plane. We will now determine the first fundamental form of the surface, which is defined above in the beginning of the section. We have that capital W in terms of x and y being the components of a complex variable. This is equal to capital W in terms of r cosine phi and r sine phi. Hence, for all values of phi, we have that capital W sub r is equal to capital W sub x then times cosine phi plus capital W sub y times sine of phi. This is all very standard stuff. On the other hand, in consequence of what we had worked out towards the end of the proof for theorem 84.1, we also have that capital W sub r evaluated at z naught equals capital A sub 1 then times cosine of beta naught minus beta 1 minus phi, which consequently is equal to capital A sub 1 then times quantity cosine of beta naught minus beta 1 then times cosine of phi plus sine of beta naught minus beta 1 then times sine of phi. And comparing this expression and what is right above it for capital W sub r, we find that capital W sub x is equal to capital A sub 1 then times cosine of beta naught minus beta 1, and capital W sub y is equal to capital A sub 1 then times the sine of beta naught minus beta 1. So we set capital Q equal to h prime over h. Then we have that capital Q evaluated at z naught is equal to lowercase a1 over lowercase a naught, which is equal to, or equivalent to, capital A sub 1 over capital A sub 0, or capital A naught, then times e to the I times quantity beta 1 minus beta naught. Hence, at z naught, we have that capital W sub x is equal to the modulus of h, then times, okay, this is German character capital R, and then capital Q. What that means, this is kind of dated notation. That means the real component of capital Q. So similarly here, we have capital W sub y equals the negative of the modulus of h, then times the imaginary component of capital Q. So yeah, it says here right below where r of q and I of q are the real and imaginary parts of capital Q respectively. By, what is 27.1? We can just click, what is that? Oh, the definition of the first fundamental form. Scalar product of vector x sub alpha with vector x sub beta, which is represented in notation as lowercase g sub alpha beta. And this vector parametric representation, x, is actually a derivative of your parametric representation. It's the first derivative in the alpha direction, which could be like U1, or it could be alpha. So, but then beta is like U2. Or you could leave it as just a beta, depending on what exactly it is you're doing. Okay, now I can get back to this. So by the definition of the first fundamental form we obtained from this, all the components and the discriminant of the first fundamental form laid out here. So G sub 1 is equal to 1 plus the square of the modulus of H, then times the square of the real component of capital Q. G sub 1, 2 is equal to the negative of the modulus squared of H. Then we have times the real component of capital Q times the imaginary component of capital Q. And G sub 2 is equal to 1 plus the square of the modulus of H, then times the square of the imaginary component of capital Q. We have the line 84.9 repeated twice in this PDF, but this is, believe it or not, the more reliable PDF. The one that's just the scans of the pages directly is missing a lot of critical pages, especially from these later chapters. So moving right along, the discriminant of the first fundamental form, lowercase g, is equal to 1 plus the square of the modulus of H, then times a quantity, which is comprised of the square of the real component of capital Q plus the square of the imaginary component of capital Q. That is the discriminant, lowercase g is equal to 1 plus the square of the modulus of H prime. We now investigate the Gaussian curvature of the surface, which we've been working with so far. So from the definition of Gaussian curvature, and actually that's not the definition of Gaussian curvature, that's the definition of the second fundamental form, because that's what all these lowercase b's are notating. So the first component of the second fundamental form, b sub 1 is equal to scalar, if you want to think of it that way, 1 over the square root of lowercase g, again the discriminant of the first fundamental form. Multiply that onto a 3 by 3 determinant. I wouldn't exactly call it sparse, but we've got 4 out of 9 entries, 4 out of 9 entries being a 0, so I'm going to read them all column-wise now. So in the first column of this 3 by 3 determinant for our second fundamental form component here, we have 1, 0, 0, and then we have 0, 1, 0 in the second column, and then in the third column we have capital W sub x, then capital W sub y, then capital W sub xx. And in all, we have then that b sub 1 is equal to capital W sub xx all over the square root of lowercase g, etc. So we can continue on and similarly find the components of the second fundamental form for this surface. In consequence of the components of the first fundamental form, which we thus laid out here, we thus obtained that the discriminant of the second fundamental form, lowercase b, is equal to, of course, as we know, b sub 1 then times b sub 2 minus the square of b sub 1 2. So in consequence of this, we thus obtain that we have, for the discriminant of the second fundamental form, a fraction with a numerator of capital W sub xx then times capital W sub yy minus the square of capital W sub xy, and this is all over a denominator of 1 plus the square of the modulus of h prime. We have to determine the second derivatives occurring in what I just read. So I guess we're just going to get right into that. Differentiating capital W sub x minus I times capital W sub y equals the modulus of h, then times the real part of capital Q plus I times the imaginary part of capital Q. Weird way of writing it that way. Why not just write capital Q? Equals the modulus of h, then times h prime over h, which works out to be capital W times capital Q, okay? With respect to x, that's what we did. We differentiated with respect to x here. We obtain in consequence of partial z, partial x being equal to 1. We thus also have capital W sub xx minus I times capital W sub xy is equal to capital W sub x then times capital Q plus capital W times capital Q sub x, which is equal to capital W then times capital Q then times a quantity, the real component of capital Q minus capital Q closed quantity, plus capital W times capital S. This is all equal to negative I times capital W, then times capital Q, then times just the imaginary component of capital Q, plus capital W times capital S, where capital S in all of what I just read is equal to H double prime over H. And differentiating the expression, what I worked out for capital W sub x minus I times capital W sub y equals capital W times capital Q, differentiating that with respect to y, we find in consequence of having that partial z partial y equals I, we find that we have capital W sub xy minus I times capital W sub yy is equal to negative I times capital W, then times capital Q, then times the real component of capital Q plus I times capital W times capital S. Here's a bread and butter trick of working with complex variables. Comparing the real and imaginary parts on both sides of the two relations, we obtain that capital W sub xx equals capital W then times the imaginary component of q squared plus the real part of s. We have capital W sub xy is equal to capital W then times the real component of q then times the imaginary component of q minus the imaginary component of s. And capital W sub yy is equal to capital W then times quantity where we have the square of the real component of q minus the real component of s. And from this all, we may now write capital W sub xx then times capital W sub yy minus the square of capital W sub xy is equal to capital W squared then times, we have this quantity where we have the real component of s then times another quantity where we have the square of the real component of q minus the square of the imaginary component of q, and then we close that inner quantity, so now we're still in an outer quantity where we have plus 2 times the real component of q times the imaginary component of q times the imaginary component of s, and then we close the outer quantity, but we're not done because then it's minus the square of the modulus of h double prime. Now the real component of h prime squared over h double prime times h in the denominator we have equal to the real component of q squared over s, so this is all now equal to the real component of this fraction, where in the numerator we have two quantities multiplied by each other. The first quantity, we have the real component of q squared minus the imaginary component of q squared plus 2 times I times the real component of q times the imaginary component of q, close that first quantity in the numerator, then times the second quantity in the numerator, which is a real component of s minus I times the imaginary component of s, close that quantity, and that's the entire numerator. Then in the denominator we have the square of the modulus of capital S. This works out to be equal to a fraction where in the numerator we have the real component of s, then times a quantity which is the square of the real component of q minus the square of the imaginary component of q, closed quantity, plus 2 times the real component of q times the imaginary component of q times the imaginary component of s. And then the denominator of this fraction is just the square of the modulus of h double prime over capital W squared. And consequently, we now have that capital W sub xx times capital W sub yy minus capital W sub xy itself squared then is equal to the modulus of h double prime squared, then times quantity, which is the real component of h prime squared over h double prime h, then minus 1, closed quantity. So by, what is it, 41.9, that is definition of Gaussian curvature. By 84.9 and 84.10, stuff we just worked out, the Gaussian curvature of the modular surface of an analytic function h of z is given by the expression capital K equals discriminant of the second fundamental form, b over the discriminant of the first fundamental form, g is all equal to, it boils all down to, the square of the modulus of h double prime, then times a fraction with the numerator of the real component of h prime squared over h double prime times h, and then the real component of that is minus 1. That's the numerator. The denominator then is the square of the quantity 1 plus the square of the modulus of h prime. From this formula, we can draw several important conclusions. We first consider the case that h double prime of z equals 0 at a certain point. We set h evaluated at z plus a perturbation eta. This is equal to expanded out lowercase a naught plus lowercase a sub 1 then times eta plus lowercase a sub 2 then times eta squared plus etc. plus the nth term being lowercase a sub n then times eta to the n plus etc. Let h of z equals 0, then lowercase a naught equals 0. Since simple zeros are singular points of the modular surface, we may assume that h of z equals h prime of z, which equals h double prime of z, which equals 0. Therefore, a naught equals a1 equals a2 equals 0. If ak is the first non-vanishing coefficient of the expansion, which I just read in terms of where we have perturbation of eta, then h prime squared over h double prime times h is equal to lowercase k over k minus 1 plus terms on the order of 1, and this lowercase k is greater than 2. Consequently, at the point z under consideration, the value of the real component of h prime squared over h double prime times h, then minus 1, is finite. We thus obtain the following result. At all points which are at least triple zeros of the function h of z, the Gaussian curvature of the corresponding modular surface vanishes. It can be proved that if a naught is non-zero and a2 is 0, then the real component of h prime squared over h double prime times h, then minus 1, has also a finite value at the point z under consideration. From the expression for Gaussian curvature for the modular surface that we've been investigating so far, we thus obtain the following Theorem 84.2. If at a point where h double prime is non-zero and the real component of h prime squared over h double prime h is greater than 1 or less than 1, the corresponding point of the modular surface of h of z is respectively elliptic or hyperbolic. If h double prime is equal to 0, or if the expression, which is the statement of this theorem, has the value 1, the corresponding point of the modular surface of h of z is parabolic. Parabolic points corresponding to h double prime equals 0 are isolated in general, while the other parabolic points form certain curves which we call parabolic curves of the modular surface. In special cases, a point corresponding to h double prime equals 0 may lie on a parabolic curve. If h double prime of z is equal to 0, then h of z equals a times z plus c. The corresponding surface is a cone or a plane. It consists of parabolic points only, except for, of course, the apex of the cone. From Theorem 84.2, we obtain Theorem 84.3. In a sufficiently small neighborhood of a pole at a point z which is non-infinity, so it's not the point of infinity like in a previous episode I brought up the Riemann spheres and Mobius transformations on the Riemann spheres. That's also another thing that I pulled from visual complex analysis. So that's, like, again, a great reference for this part of the book. So in a sufficiently small neighborhood of a pole at a non-infinity point z, the modular surface of h of z consists of hyperbolic points only. The proof is as follows. Without loss of generality, we may assume the pole to be at z equals 0. We denote by k its order, lowercase k, that is, not to be confused with capital K for Gaussian curvature. Then h of z is equal to a sub negative k and then times z to the power of negative k plus etc. And then we have h prime of z equals negative k, then times a sub negative k, then times z to the negative k minus 1 plus etc. And h double prime of z is equal to k, then times quantity k plus 1 closed quantity, then times a sub negative k, then times z to the negative k minus 2 plus etc., where in all of these a sub negative k is non-zero. We also have now h prime squared over h double prime then times h equals lowercase k over lowercase k plus 1 plus small o of 1. So this is a power series which at z equals 0 has the value lowercase k over lowercase k plus 1. From this and the previously read Theorem 84.2, the statement of Theorem 84.3 follows. And I'm going to do a little bit of a recap at the end here, if I get to the end. We now consider the curvature of the surface in the neighborhood of a point which corresponds to a 0 of h of z. Theorem 84.4. If z0, again, not an infinity point, is a multiple 0 of h of z, the points of the modular surface of h of z which correspond to z, where we have this, I don't know, you would call it like a disk in the complex plane. 0 is less than the modulus or magnitude of the difference between z and z0, so z minus z0. Then that's less than epsilon, and this epsilon is greater than 0, and sufficiently small r elliptic. So I'm going to read that one more time. If z0, not an infinity point, is a multiple 0 of h of z, the points of the modular surface of h of z which correspond to z, where the distance between z and z0 is bounded by epsilon, is sufficiently small, r elliptic. If z0 is a simple 0 of h of z, then on the portion of that surface corresponding to where z is less than epsilon away from z0, there exist 2k minus 2 angular regions whose points are elliptic or hyperbolic points. Lowercase k is the exponent in the first non-vanishing term after the linear term in the power series development of h of z at z0. The proof is as follows. Without loss of generality, we may assume the 0 of h of z to be at the point z equals 0. If z equals 0 is a multiple 0, h of z is of the form where we have h of z equals a sub m then times z to the m plus etc., where a sub m is non-zero and m is greater than or equal to 2. Therefore, h prime of z is equal to m times a sub m then times z to the m minus 1 plus etc., and h double prime of z is equal to m times quantity m minus 1 closed quantity then times a sub m then times z to the m minus 2 plus etc., and h prime squared over h double prime times h is equal to lowercase m over lowercase m minus 1 plus small o of 1. From the fact that in a sufficiently small neighborhood of the point z equals 0, the real part of this expression is greater than 1, the statement concerning multiple zeros follows. If z equals 0 is a simple 0 of h of z, then h of z is of the form h of z equals a sub 1 times z plus a sub k times z to the k plus etc., where a sub 1 is non-zero and a sub k is non-zero. Therefore, h prime of z is equal to a sub 1 plus k times a sub k then times z to the k minus 1 plus etc. h double prime of z similarly is equal to k times quantity k minus 1 closed quantity then times a sub k then times z to the k minus 2 plus etc. And the real component of h prime squared over h double prime times h, which is equal to the real component of a fraction where we have a numerator of a sub 1 then times z to the 1 minus k all over a denominator of k times quantity k minus 1 closed quantity times a sub k then times quantity 1 plus small o of 1 close all quantities. This is equal to a fraction with a numerator of capital A sub 1 then times r to the 1 minus k all over a denominator of k times k minus 1 closed quantity times capital A sub k. That fraction is then times cosine evaluated at beta 1 minus beta k minus the quantity k minus 1 closed quantity times phi. That's what the cosine is evaluated at. Then the third term of what is being multiplied together to get this real component of our h prime squared over h double prime h. The last term is then the quantity 1 plus small o of 1. And we can refer back to things that we previously calculated in this section. So since this expression increases arbitrarily if r approaches 0, the type of the curvature depends on the sign of the cosine. The values phi, for which we have that beta 1 minus beta k minus the quantity k minus 1 closed quantity times phi equals pi over 2 times the quantity 2n plus 1, that is, phi is equal to a fraction with a numerator of beta 1 minus beta k over a denominator of k minus 1, and then this is minus another fraction with a numerator of pi times the quantity 2n plus 1 all over a denominator of 2 times the quantity k minus 1 closed quantity, where in all this being said, k is lowercase and greater than or equal to 2. These values of phi correspond to the zeros of the cosine. These are the directions tangent to the parabolic curves at z equals 0. These curves are the boundaries of portions of the neighborhood of z equals 0 containing either only hyperbolic points or only elliptic points of the surface. This completes the proof. As simple examples, we finally consider the functions sine of pi of z and the cosecant of pi of z, which, as you're probably already familiar, is equal to the reciprocal of the sine of pi of z. And we see these depicted in figures 87, 88, and 89. I'm going to flash these by really quick and say, these look really interesting, but actually the pictures in visual complex analysis are going to be a little more interesting. The orthogonal projection of the modular surface of cosecant of pi of z onto the xy plane can be obtained from that of sine of pi of z. And we can see this in figure 88. Maybe I'll splice that on screen. By replacing capital W by 1 over capital W and lowercase gamma by negative gamma, the zeros of sine of pi of z at z equals 0, at plus or minus 1, plus or minus 2, etc., correspond to poles of cosecant of pi of z at these points. The parabolic curves, which correspond to the dotted lines in figure 87 of sine of pi times z, are the solutions of the equation which is the real component of the cotangent squared of pi times z being equal to -1. The parabolic curves of the cosecant of pi times z are obtained from the equation of the real component of cosine squared of pi times z over the quantity 1 plus cosine squared of pi times z, close all quantities, all being equal to 1. These curves are the boundaries of portions of the surfaces consisting of hyperbolic or of elliptic points only. And to finish things off from the Kreisig book, from what we had calculated above, it follows that the analytic functions whose modular surfaces are developable are the exponential functions h of z equals the exponential of a times z plus b, and the powers h of z equals quantity a times z plus b closed quantity to the power of 1 plus I times lowercase k, where a, b, and lowercase k are constants and lowercase k is real. And like I promised, here's some more interesting figures from visual complex analysis. So figure 14 is reminiscent of figure 89, but we have, looking at the caption here, this is obviously just like a sketch. So props to whoever did this sketch back in the day. But we have z equals x plus iy, then we have x, and then we have y. And then these correspond to the poles where it's supposed to be going off to infinity. Maybe it's a little more crisp and a little more obvious what's going on in this modern computer-generated figure here. We also have, okay, from the Kreisig book, figure 87, figure 88. We're looking at the modular surface of sine of pi times z. And then we have this orthogonal projection. We're like, you know, this is maybe not the best way. Not all encompassing. We can scroll through here and I'll let you be the judge. Take a gander at figure 25 from visual complex analysis. We have just normal sine of x. Then we have hyperbolic sine, hyperbolic cosine. That's a pretty slick take. And then to really cap things off, now I think, you know, we're having a kind of reprise of a moment that occurred in history 2,400 years ago when Plato wrote down the lessons of Socrates. It was kind of a taboo thing to do. They were really emphasizing spoken word language and memory from like an intellectual vogue point of view. And so for Plato to write everything down, the criticism was like, well, whatever was great about having everything just in your mind's memory and then being able to orally articulate that. Whatever's special about that is kind of lost by writing things down. You do gain, however, by writing things down, things are set in stone, right? Maybe that's, intention, pun intended, right? And the information can pass on in a more conserved manner. It's less error prone that way. So now here we are in 2025 and we have AI coming out, and you can kind of make the same sort of finger wagging puritanical sermon. But really, it's been echoing since like the early 2000s, like you could say, or even earlier than that, like computers now and having things like pocket calculators diminishes your ability to do just like mental arithmetic, right? And having a computer and having the ability to look up things on Google, well, now you don't sit around and you're daydreaming at work and you say, oh, how do we handle modular surfaces of analytic functions, and how does that all relate when we dress it up in terms of differential geometry with first and second fundamental form, and we're going to investigate things like Gaussian curvature, but we want to still keep it in the complex variables world. You could be daydreaming about it at work, and then you get this burning desire. You don't just say, I'm not going to worry about that stuff, I'm going to get back to work. Instead, you have a burning desire to remember or figure out or learn about these things. And so you go to the library and you look for the books, and maybe they don't have the books, someone else checked them out. So you have to reserve the books, and you have to wait several weeks for whoever had it checked out to get called by the library, and they say, hey, bucko, you can't renew the complex analysis by Lars Alfors infinitely anymore. You have to return it to the library so that this guy can check it out for 2 weeks and he can look up what he's had a burning desire at work to remember about complex variables. Oh, okay. You wait, you get the book you reserved, you peel it open, you read what you wanted, maybe you write down by hand parts of the section. Maybe there are no photocopiers available, Xerox machines, right? In this thought experiment. And then you've got whatever you were looking for at that moment you were daydreaming. But now we're jaded, right? Because you could be daydreaming at work and you could just be like, oh, I'm just going to Google, go on Wikipedia. Oh, that's, the statement of residue theorem. Or, oh, that's the, Weierstrass function definition or whatever it is, right? And then you don't have to have that burning desire where you spend weeks just like grinding your teeth in anticipation over figuring out something that was bothering you weeks ago, right? And now, in the day and age of AI, it's like you don't even need to really like learn a lot more or articulate very much, because what you get out is just already relatively so crisp and put together. But that's the risk, right? Is that now I've noticed, maybe you have as well, sure, you can ask big questions like fill in the gaps of Bernard Riemann's habilitation thesis, but mileage may vary. Last video, ask it to prove a theorem. It's not a big deal. It's kind of like a routine kind of exercise of a theorem proof. But, AI can guess wrong about what's the definition of translation surfaces with isotropic generators, and based upon that assumption that it made, it works out a slop answer. But then sticking with being all crisp and clean, it's like, oh, well, we can interpret this away, and it just kind of does this hand wavy, these aren't the droids you're looking for. And if you're not careful and you just run with the answer that you're given at that point, then you might run into problems. But with my whole boomer rant aside, it is very useful to, say, be in a time and age where you can, I'm not going to say what website, but you can go and download a PDF of a textbook And then you can just copy all the text in your section, hit Control C, and go over to your AI, Control V, and then be like, summarize this section, but what you want to do is then also tack on and be like, compare and contrast the methods used to prove the theorems in that section. So it's like everything that I just said could relatively have been word salad for you, right? But then when you put that into Chat, GPT, Grok, Claude, whatever it is, this is what I got out. So theorem 84.1. So regularly on the first half to the image point this one give tables on and simple entering over with. That's what I put in the proof, and then you get out. The proof uses the directional derivative of capital W. Again, that's the modulus of h of z. Leveraging the analyticity of the given function h of z to compute slopes and analyze singular behavior at zeros. So that, I feel like, is maybe more helpful than reading back the statement, reading back over the proof, because then you're at the high level 10,000 foot view of mathematics, so-called, where you say, okay, when you're in the wild and you're handed these surfaces or analytic functions, which you could think of as surfaces, a thing you can do is to compute these directional derivatives, make considerations about, is your function analytic in the domain that you're considering it in, and look at the slopes, look at the singular behavior around these given points around your poles and stuff like that. It's like, okay, that's like a technique that you can maybe put in your back pocket at the end of the day and, do stuff later on down the line with. Going on, theorem 84.2. I don't think we actually had a proof of that, a formal proof, but it was kind of like a classification proof, right? It's stuff that we've seen in differential Riemannian geometry before. We have Gaussian curvature computed everywhere in your domain or on your surface or whatever, your surface of your analytic function, modular surface, compute your Gaussian curvature everywhere, and then say, where is it positive? Where is it negative? Where is it equal to 0? That was theorem 84.2. And theorem 84.3. In a neighborhood of a pole of h of z, the modular surface consists of hyperbolic points only. This one, as I just read, we did do a quick proof of that one, if I'm not mistaken. And it was really straightforward. The proof uses the Laurent series expansion near a pole and then applies theorem 84.2's curvature criterion. So it's like, okay, we didn't do a full proof of 84.2, but tied into 84.3 so that 84.3 has a little more proof substance, if you will. Then we have 84.4. I'm not going to read it out again, but the key method then, according to our AI output here, is the proof uses power series expansions and the Gaussian curvature formula, which we derived in this section, to analyze the behavior near zeros. So I don't know about you, but then it's like, I don't feel like we allowed ourselves to have our hand held throughout this, because yeah, it is true. All of the solutions are in the back of the book, and you can just verbatim read out loud the sections and stuff like that. And it's like, oh, it's reading differential geometry out loud by Erwin Kreisig. But the more work you put in, the more you get out, right? So with using AI as a tool, it's no different. It's the same as like using a calculator when you're in like middle school algebra or something like that. Yeah, if you always use a pocket calculator, you're never going to learn a multiplication table. And then you go to undergrad, same thing. If you're in statistics and you overly rely on the formula sheet in order to pass your statistics exam, well then when you go to grad school and you meet a postdoc and they, aren't in the same project, but they're like, hey, grad student, what do you think about, the analysis of variance and the p-values of your last experiment or whatever? And you're drawing blanks on you're stuttering about statistics terminology and stuff like that. It's a bad look. And it's your own damn fault for overly relying on formula sheets at that point. So now here we are. We're reading differential geometry as so-called adults, and it's like you can choose to use AI to further hold your hand even more to get through a book where all of the problem solutions are in the back of the book already. It's like, what a time we live in, right? We don't even have to find like some pirated, cracked solutions manual with only the evens or something like that, and it's frustrating. You just ask AI and you can get at least a swing at the bat of like something that looks like the correct answer, right? And so it's like, have some maturity and discipline, and go into the details of the answer and be like, oh, Grok made a mistake, and if you just look at the bottom of the output, it may seem like you've got the legit math, but like you really don't. And so that's what it means to be a legit mathematician maybe in this day and age. I don't know. Go watch a Terrence Tao podcast with Lex Friedman. It's a good podcast. Anyways, see you guys in the next one.